Hello, grade 10s. Welcome to this first online lesson with Mr. G. Today we're going to be covering radiation. We're going to start off with isotopes. What are isotopes? And we're going to end off with three forms of radiation: alpha decay, beta decay, and gamma decay. So if this is your first time hearing these terms, alpha, beta, gamma, I'm going to make this as simple as possible for you by just giving you a magic formula that will help you answer a lot of these sorts of questions. Let's start off with isotopes. So we have isotopes. I'm just going to highlight it. Isotopes are two or more forms of the same element with the same number of protons but a different number of neutrons. So in our periodic table, there are a bunch of elements: hydrogen, oxygen, carbon, nitrogen, calcium, and so on. Often at times, or there is, some elements that have different versions of that element that differ based on the number of neutrons. So let's look at hydrogen for an example. Isotopes of hydrogen. In this diagram, I've shown three isotopes of hydrogen: hydrogen 1, hydrogen 2, and hydrogen 3. These hydrogens, they differ based on their number of neutrons. Next, let's look at an example of isotopes of carbon. So this is just a random element where I'm just giving, just as a random example, carbon. There are different versions of carbon. The normal version that we know is carbon-12, 6, where there's 6 protons, 6 neutrons, 6 electrons. That's the version of carbon we know. It's on the periodic table. But there's also about, I think, 15 to 20 other versions of carbon that have different number of neutrons. I'm only going to draw 2 other ones, which are carbon-13. Now, carbon-13 has 7 neutrons, and we're also going to draw carbon-14, which has 8 neutrons. So just like hydrogen, there are different versions of carbon. That's what an isotope is. It is one element that has different neutrons. Next, if isotopes have too many neutrons, what happens if you have too many neutrons? They have too much energy, or they may have too much energy, and therefore they can be unstable. Isotopes that are unstable are called radioactive isotopes. Next, let's say we find ourselves a radioactive isotope. That isotope, that element, that version of an element, it has a lot of energy. It needs to get rid of that energy. So how does it get rid of that energy? Well, there are 3 ways. Alpha decay. Well, there are more than 3 ways, but these are 3 of the most simple ways. Or these are the 3 ways that you're covering in grade 10. Alpha decay, beta decay, and gamma decay. So just to read the definition, radiation is a mechanism of energy transfer in which atoms or molecules give off energy in the form of electromagnetic waves. The 3 most common forms of nuclear radiation are alpha, beta, and gamma decay. Now, let's go through each one in a little more detail, and I'll give an example for each one. So alpha decay first. Alpha decay. Alpha decay occurs when an atomic nucleus emits an alpha particle, which is the same as a helium nuclei. And the example will help you understand this better. The resulting nucleus has a mass number reduced by 4 and an atomic number reduced by 2. An alpha particle, because it's a helium nucleus, has a +2 charge. So let's look at an example. We have the example. It says, show the alpha decay of radium-226. So this example has already been completed for us. You see radium-226, right? One second, let me just get my pen. Radium-226. The mass number, or the atomic mass, is 226. So I'll just write atomic mass. And the proton number, the atomic number, is 88. I'll just write atomic number. Oh, my writing is a little messy. It says atomic number. The question asks, show the alpha decay. So if you look at the products, immediately you'll notice an alpha particle or a helium nucleus. That has to be one of the products if it says alpha decay. Now the question is, how do you get the other element? What steps do you need to take to get the other elements? So my way of thinking about these sorts of questions is to balance the numbers, to conserve the mass. The proton number, the mass number, it can't change before and after the reaction. That's my way of thinking it. So if you look before the reaction at the atomic mass, I'll just get another color, it's 226. 226. So after the reaction, the atomic mass of both of the products also should be 226 if we combine them together. And what do we have? We have 222 and 4. If you add them together, you get 226. And we can do the same thing with the proton number. We have 88 in the radium. And on the daughters, you have 86 plus 2, which is also 88. So that's how you do alpha decay. Let's go through another example to better understand this. So we have, I'll just get another color. The question asks, show the alpha decay of the francium-211 isotope. So first off, francium-211. That's the very first thing you should do. The next thing you should do is you should check your periodic table. What is the atomic number of francium? And I'll just Google this real quickly. It's 87. So that's the first step. The question says show the alpha decay. So let's draw our products. Immediately we know one of our products has to be a helium nucleus, which is always 4-2. And you could draw an alpha symbol, or you could draw a helium, the HE letters in the previous example. And the question is, what's the other product? What's the daughter? So the numbers need to balance. On the left side, we have 211. So on the right side, 4 plus what equals 211? So it would be 207. And if we do the same thing in the bottom, you would get 85. 87, francium, the atomic number of francium is 87. So the two products on the right side, they both need to add to 87. One of them has to be 2 because that's the alpha particle. The other one would be 85 because 85 plus 2 equals 87. The last thing you need to do for this question is figure out the element. Which element symbol do we put? If the atomic number is 85, you can go to your periodic table and see which element it is. And in this case, it would be astatine. 18. So that's alpha decay in a nutshell. Next, let's move on to beta decay. So in beta decay, it's the same idea, but instead of emitting an alpha particle, now the parent element or the parent isotope is now releasing a beta particle. So beta decay, it's now releasing a beta particle, which is a fast-moving electron, and a beta particle has a -1 charge. So let's look at an example. The first example, lithium 8,3 produces beryllium 8,4 and an electron. So once again, we know one of the products has to be an electron because it says beta decay. The question says lithium 8. So that's where we got the Li from. Li is lithium. The lithium 8, that 8 stands for the atomic mass, which is up here. And the 3 is the atomic number of lithium. You can find that on the periodic table. And it's the same idea. The numbers, they add up. So for the atomic mass of lithium, we have 8. Beryllium also has an atomic mass of 8, and electrons, they don't have an atomic mass, or the mass is so little that we just write it as 0. And same thing for the atomic number. Lithium has 3. The atomic number is 3. It has 3 protons. Beryllium, the number would be 4 because electrons have -1. It's a -1 charge. So 3 equals 4 plus -1. 3 equals 4 plus -1. I just put brackets around it. That's where we got the 4. So let's do another example looking at carbon-14. So we have step 1, write out the element that is undergoing radioactive decay. Carbon-14. What we have to put a number here. That number is going to be found on the periodic table. Carbon, the atomic number is, I think it's 12. Let me just double check. The atomic number is 6. Sorry, it's 6. The atomic mass is 12. It's undergoing beta decay. So we know for sure if it says beta decay, one of the products is going to be an electron. And the other product, you would do the same method as we did for alpha decay. You'd add the numbers. So on the top, you would have 14 equals 0 plus 14. On the bottom, you'd have 6 equals -1 plus 7. And finally, you have to write the element name. And the element name you can get by looking at the atomic number. In this case, it's 7. So nitrogen. That's beta decay. If you have any questions, you can add it in the comments below. And finally, last but not least, gamma decay. Gamma decay is probably the easiest, and I'll explain why. So for gamma decay, let's read the definition. After alpha or beta decay occurs, a nucleus is often left in an excited state, so it is unstable. So this is after alpha or beta decay. To become stable, the nucleus gives off high energy photon called a gamma ray. A gamma ray has no electric charge. That is what gamma decay is. Let's look at an example to understand this a little better. So we have, in our example, show the gamma decay of uranium. This should say 235. So we have, in the example, uranium 235. To show the gamma decay, the first thing you do is you draw a gamma ray, which looks like this. It's a photon, so it has no charge, no mass. And then you use that addition method I was talking to you about in the previous beta decay and alpha decay examples. You add the numbers so they match. In this case, because gamma decay is both 0 and 0, you'll notice the element is the same. That is gamma decay. Often at times there's a star to indicate that it's unstable. That star, if you see in questions, is just showing that that element is unstable or that isotope is unstable. So let's do another example of technetium. So technetium, Tc99, becomes, and we'll add a star here just to show that it's unstable. Technetium, the atomic number is 43. So it's going to undergo gamma decay. If it says gamma decay, the very first thing you should do is draw a gamma particle. 0, 0, and the gamma particle is kind of hard to draw, but you can practice it a few times. Something like that. And because the numbers are 0, 0, we're next going to add across to match the atomic mass and the atomic number. In gamma decay, the product, the daughter, is the same. That's gamma decay in a nutshell. So hopefully from this video, you were able to understand what radiation is. You were able to understand the 3 forms of radioactive or nuclear decay. And that's that. Thanks for watching. I hope you understood this material better. And if you have any questions, once again, just add it in the comments below. Thank you so much.